Good morning. This is AP Statistics Friday morning, and we have a continuation of the lesson starting with inferences about means, part 2 of 3. Take that out. We're on the last problem, and while you're pulling that out, I just want you to know that there is a homework assignment due on Monday, so there's 2 handouts you want to get from the substitute teacher who's here in the room. One of them is the assignment sheet for Unit 10, and sure enough, homework number 1 is due on tax day, 4/15, and wow, tax day, I have to have my taxes done on Monday. Okay, so 4/15, and then homework 2 and 3, we're having the test 1 week from today, next week, Friday. All right, so the other handout that you'll need is the inferences about means, part 3 of 3. The homework assignments, there's a few homework assignments I've not put in the book yet, so I'm going to put those in as effort grades, 6 points each. And the homework that's due on Monday, all of the Unit 10 homeworks are going to be worth 12 points instead of 6, and they'll be graded not on effort, but graded based on accuracy. So you know, there will be some places where you need to pause through the homework, but we're on number 20, late arrivals. Let's pick up where we left off. Will your flight get you to your destination on time? And we have some data. It's in the table and in the histogram. The histogram is given to you so you can verify that it's unimodal and symmetric. What you're supposed to do is go to your calculator and type that given information of the mean, the standard deviation, into Stat Test 8. We're putting the 8 in AB 80, 56, 24. In Stat Test 8, we select statistics. We take the mean from the table Y bar and type it in as X bar. Our book uses Y bar instead of X bar for some reason. The sample standard deviation from the table is placed into the calculator, 4.08837. The sample size is 144. They're asking for a 99% confidence interval, so we type in 0.99 and press calculate. So this is where we left off class on Wednesday, the last time we met, and sure enough, the confidence interval is, just as it says here, 19.19, 20.97. So Stat Test 8. Interpreting that interval, we say we are 99. Actually, the box statement is left out, so let's put that in. Based on the sample, we are 99% confident that the interval from 19.19% to 20.97% contains the true mean monthly percentage of on-time flight arrivals. Friends, this problem is messing with your mind because usually we say, well, we've got Z is for percentages or proportions. Z is for proportions. T is for means always. So notice what the mean is. It's the mean percentage on time arrival rate. What's the average percentage? So sometimes students get all flustered. It's like, wait, am I supposed to be using Z for proportions or percentages or T for means? Well, you got to read it carefully. They are asking for the true percentage of flights that may arrive late. And the true, it's like, what's the average percentage? So the signal is right here. Y bar is the average percentage, but ultimately it's a mean. And so 20.07 is the mean. So that's why we're using T for means instead of Z for proportions. So you have to just be careful. Notice that we are finding the mean percent, which is potentially very confusing. So I'm going to give you a flashcard problem. Oftentimes we've done the flashcard problems in a GFA format. This time, since you're just watching this video on your own, I would like you to, actually I want to find the problem that I actually want you to do. It's this one. This is the problem. So I'm going to read it. After I finish reading it, I want you to pause the video and try to solve it on your own. It says, A fitness center advertises that the average pulse rate of its members is 68.4 beats per minute. A high school AP statistics instructor suspects that this is a made-up number. I just made that up. And so he runs a hypothesis test on a simple random sample of n equals 48 members, calculating a mean, the mean of x bar equals 71.0 beats per minute with a standard deviation of 10.3 beats per minute. In which of the following intervals is the p-value located? We've got A, B, C, D, and E. So go ahead and pause the video, work this out on your own, and select either A, B, C, D, or E. We're back. By the way, here's how I would work this. I would, first of all, recognize that we're looking for a mean. So I need a test statistic in the form T equals X bar minus mu sub 0, the hypothesized mean, over the standard deviation is S over the square root of n. Now, see, these are means, so the central limit theorem comes in handy. We're thinking in our minds about a sampling distribution of sample means. And that didn't just happen, so we're going to go select and lock. Now, the other thing to keep in mind is that when you type in, this could all be done on stat test 8. But if you're doing it, those of you who did it by hand, you're probably thinking that the null hypothesis is going to be, one more time, that the null hypothesis is going to be mu equals 68.4, what they said. We think it's a made-up number. We don't know if the truth is greater than or less than, so the alternate hypothesis does not equal. This is going to be a two-tailed test. So does not equal 68.4. I would expect you to draw a picture. Hypotheses. The model is going to be a student's T model with 47 degrees of freedom. The hypothesized mean is 68.4. We observed 71. And you'd have to find the difference between 68.4 and 71, subtract and get that number. I don't really care what that number is, but the p-value is going to be the sum of these two areas. So to calculate the p-value, I need the probability that we observe a test statistic as extreme as the test statistic associated with 71. That t-score, by the way, would be 71 minus 68.4 divided by the standard deviation, which was given as 10.3, divided by the square root of the sample size, 48. So that's the test statistic, comma, 999, comma, 47 degrees of freedom. So, I'm actually mixing calculator notation with written notation. So what's the probability that we get a test statistic greater than this? So the test statistic that is this t-value or greater, so we would say this is going to be t sub, I'll give it a name, you can call it the test statistic, and the observed test statistic has got to be greater than this. So what's the probability that t is greater than this number, given that the test statistic is equal to 0. The test statistic associated with this number is 0. If you type this into your calculator, the test statistic comes out to be 1.748. That is 1.748. So a slightly less cumbersome representation of this would be, what's the probability that the test statistic on 47 degrees of freedom is greater than 1.748, given that we have a mean of, the true mean is 68.4. So we also have to multiply this by 2 because it's two tails. Now, if you're doing this in a race situation, you probably just want to go to TCDF. This is one way to type it in. 2 times TCDF of 1.748, comma 999, comma 47 degrees of freedom. And that would give you a p-value of 0.087. So 0.087, we've got looks like letter D. Now, another way to get this is probably the fastest way to get this if it's calculator allowed. And of course it's calculator allowed because everything in AP Stats is calculator allowed. You can just go to a stat test. Let's see, we're getting a p-value from T. So we're thinking AB 80, 56, 24. So put a 2 into AB 80, 56, 24. So if you just do a stat test 2, we should be able to knock this out. The hypothesized mean, let me make this a little bit bigger for you. The hypothesized mean is 68.4. And the observed mean, the sample mean is observed at 71. The sample standard deviation was 10.3. The calculator is going to divide by the square root of 48 for us. It's a two-tailed test because we just think they're wrong. And if you go to calculate, it should give the same answer of p-value 0.087. So that's the same value that we obtained using TCDF. But by far the fastest way to do this problem is using stat test 2. So this is all leading up to today's new lesson, which is basically putting the 5624, putting the 2 in A, B, 80, 56, 24. We're going to be doing the t-test for means. This is a one sample t-test for means, and this problem kind of prepares you for that. Okay, here's the answer. And if you had pressed pause at just the right time, you would have seen the answer earlier in the video because I was showing you the screen for a second. This next problem says, what's the probability of a type 2 error? Try that one on your own, and then we'll... Okay, this one's got to be letter E. There's insufficient information to answer this question because there's no mathematical relationship between alpha and beta. Alpha does not equal some function of beta. So there's just not enough information. You would need to know power. If they gave you power, since power is 1 minus beta, then you could have calculated the probability of a type 2 error. Beta is the probability of a type 2 error. So if they had given you power, you would have taken beta is 1 minus power, but they didn't. It was insufficient information. Okay, so let's take a look at our new handout. This is, get this handout from the substitute. Inferences about means, part 3 of 3. We've got some review up front here, which is interesting and all, but I just want to let you know that I'm not sure if the blanks, let's see if this is the version that you have for the blanks. Yeah, okay. So if we're going to give you the meaning of 95% confidence, then we would say in repeated sampling, about 95% of samples of the same size and generated using the same method will produce confidence intervals that capture the true mean income of all households in District 125. So that's how the blank should be filled. And these are review formulas. Try this thing on the bottom on your own. I'm going to pause the camera while you write down the calculator notation for finding, by the way, there should be a star right here, for finding T star sub n minus 1 with a 92% confidence interval. So use your calculator. And we're back. Hopefully you used inverse T. Inverse T of, and we need left area. So 92% of the area is 0.92. Here the other 8% is split 4% in each tail. So 96% is to the left of T star sub 79. So to find T star sub 79, the critical T value, you would do inverse normal of left area is 0.96, comma 79 degrees of freedom. Now, for students who are using the inverse T program, just press program. There's one student in the year 20 19. Who has this? We just press program inverse T. When it prompts you for a P, type in 0.04. So P question mark, type 0.04. And when it prompts you for degrees of freedom, type in 79, press enter. It'll give you the same answer that we get here, which just to verify, when you do, there it is, inverse T of something went terribly wrong. My mode must be, my stat wizard must be on. It's very embarrassing. Usually the stat wizard is off, classic mode. So when we go to the distribution menu and do inverse T of 0.96 with 79 degrees of freedom, the answer is 10.641 approximately 10.641. Let's go to our main problem here. It's TV safety. Pretty important problem. Sometimes back in the old days, like 10, 15 years ago, TVs were really heavy. People would buy furniture, call it a TV stand, put the TV on. In fact, I remember students coming into class the day after the Super Bowl one year when there was a Super Bowl commercial for insurance, insurance for when some member of your family dies, and there was they had these images that, people are watching the Super Bowl, and students came in the next day, they're very upset because there's this one image of a television that had fallen over, and apparently some child had gotten crushed by this. It was all implied. It wasn't gory or anything, but that's the context here. Back before TVs were just hanging on your wall, and they very rarely fell on people. The manufacturer of a metal TV stand for home TV sets must be sure that its product will not fail under the weight of the TV. Children could get hurt. So some larger sets weigh nearly 300 pounds. And the, And the company's safety inspectors have set a standard of ensuring that the stands can support an average of over 500 pounds. So on average, so we're talking about a null hypothesis that the mean is, even though it's over 500 pounds, we say, always have an equal sign on the null hypothesis. The true mean is assumed to be 500, and so we assume it's safe. And if there's sufficient evidence that, oh wait, hold on, no, we're actually assuming that they're weak, because they test the hypothesis that they're going to break at 500 pounds, which is unsafe. If it breaks at 5, because we want them to support over 500 pounds. So we're going to assume that they're weak, which is, we're going to assume that they are unsafe, and only if we get evidence that the mean amount of weight that they can support is above 500 pounds, will we certify these TVs as safe. There needs to be sufficient evidence that these televisions are safe, otherwise we simply will not certify them. So, this upper tail, lower tail test, clearly it is an upper tail test because of the greater than symbol in the work there. So, yeah, we are performing an upper tail test. They need to prove that the stands will support 500 pounds or more easily. Explain what will happen if we commit a type 1 error. And I want you to pause the camera here and then try to fill that in. Type 1 error in context. And we're back. So the inspector has committed type 1 error. Okay, so remember, type 1 error, that's incorrectly rejecting the null hypothesis. Null hypothesis is unsafe. Reject it. We say we're declaring that they're safe. If we commit a type 1 error, if we certify the stands as safe, certify stands as safe, when in reality they are unsafe. That's pretty serious. That's a pretty serious error. What will happen if the inspector commits a type 2 error? By definition, type 2 error is, go ahead and pause the camera and try to fill it in. When you're done, come back. We're back. So the type 2 is incorrectly failing to reject the null hypothesis. So we didn't reject the null hypothesis. We declared them unsafe when in fact they were safe. So we threw it away. We threw away a perfectly good TV stand, even though it was safe. So we can word that as follows. They decide stands not safe are not safe, when in reality they are safe. TV safety revisited, number 27. Now, the manufacturer of the metal TV stands in exercise 25 is thinking of revising its safety test. If the company's lawyers are worried about being sued for selling an unsafe product, should they increase or decrease the value of alpha? Okay, so let's draw a picture to understand what's going on. Remember, we've got, they're worried about being sued for selling an unsafe product. So, selling an unsafe product, what type of error are they concerned about? Just think that through. Before I explain, if you want to pause and figure it out on your own. Are they concerned about type 1 or type 2? So here we go. If they declare it unsafe, if they declare it safe, but it's actually unsafe, declaring it safe means they rejected the null hypothesis. And yet they, but it was really unsafe. So in terms of a two-tiered picture, let's just draw a two-tiered picture of what happened. They declared it unsafe. Remember, the assumed mean is 500. Mu equals 500 pounds. And the alpha level is up here because it is a one-tailed test, alternate hypothesis. So if it's unsafe, then that means in reality, it's, let's say it only holds 400 pounds. Well, occasionally one that holds only 400 pounds will rate out up here in this region. But the point is that a type 1 error is the probability of doing exactly what they're talking about. So alphas, it's not a type 2 error that they're concerned about. They are concerned about a type 1 error. So if they want to decrease the probability of declaring unsafe products safe, they should decrease the value of alpha. I mean, if alpha is equal to 0.05, then that means 5% of the time they're going to declare unsafe stands safe. If they want to, and then they might get sued. So if they want to bring that probability down, bring alpha down. And in this case, what's meant by the power of the test? The power of the test, 1 minus beta, is basically the probability. It's always of correctly rejecting the null hypothesis. If the null hypothesis is that it's unsafe, so it's the probability of correctly certifying safe TV stands. Page 3. Now, suppose they want to increase the power of the test. What options does it have? Okay, there's 4. And there's 4 crucial concepts behind these 4 parts of the problem. So let's take them one by one. The picture here that I think will be helpful for you, we're going to assume mu is 500. But, so that's if it's weak. If it's strong, if the TV stand is strong, then suppose in reality that it'll hold 600 pounds of weight. And I'm going to lock these in. Those are not going to move. And then we decide where to put our, I'm going to make this a vertical line that's fairly thick, easy to see. So that's going to be where the alpha level is. This marks off alpha, probability of a type 1 error. Here's beta, and here's power. And then they're asking us about power on this problem. So we want to increase the power. Well, if you play with this diagram in your mind, increasing the power, increasing the probability of certifying safe stands as safe. You can see it graphically means we want, one way to do it is just to move as far this way. We want power, the area in this region, to increase. So one way to do that is we could actually make the stands stronger. Now, what does that mean in the context of this diagram? I mean, instead of moving this bar, which is somewhat artificial, just changing standards, one way is, I'm going to have to unlock this a little bit. This piece has to be unlocked so I can move this around. Okay. We could make the stand stronger. So instead of 600, we could actually redesign them so that they can hold 700 pounds on average. So one way to increase power is to redesign the stands. That if I move this bar over, now I see what I want to do in terms of selecting. I want to select all this and group it so that when let's unlock that. So you can actually see what's happening mathematically, group this. So to make the stand stronger, sure enough, instead of 600, we're moving to 700, 800, 900. That would increase power. We can see it in the diagram. However, that would require, we could increase the mean amount of weight. This is the word mean that stands can hold. Now, that type of redesign is expensive. It's like, wow, let's start from scratch and just make it stronger. We can spend a lot of money and fewer people will get hurt. Let's do this. No, we're not going to do that. It's too expensive. I mean, it would work, but there's three other options. Another option is could redesign the stands. Redesign. Sounds scary. Redesign the stands so that their strength is more consistent. Consistent as measured by the standard deviation. Why would this work? If we go back to the diagram, if we make it more consistent, then the curve would have a smaller standard deviation. And as you can see, more of the area, beta would be really small if the standard deviation came down. Beta would be small, and so power, which is 1 minus beta, would be much larger. That would increase the power. But we don't want to go that route because that also is very expensive. Here's how we say that. Redesigning the manufacturing process is likely to be quite costly. Quite costly. As if, it's quoting Garth from Wayne's World, as if we're going to do that. Think as if that phrase was originally Immanuel Kant, who said that he agreed with Hume, saying that, yeah, there's no way that we can establish cause and effect through sense data, but we have to act as if we actually are in touch with reality. So a lot of postmodern thought rests on Kant's use of the phrase as if. But for most of you, you just think of Garth from Wayne's World. And then furthermore, the company could, and this is a third way to increase power, we could increase the number of stands tested. We could just test a large number of stands that with a bigger sample size since the standard error of the sampling distribution of sample means is sample standard deviation S over the square root of the sample size. With a bigger N, that would be a smaller standard deviation overall, or a smaller standard error overall. That would have the same effect as redesigning them. But that costs more time, or that costs more money also. It costs both time to perform the test, and money to pay the quality control personnel. What do you think of this plan? Whatever. Like, more money? Not going to happen. And then a fourth option is the company could increase alpha. Check this out. How do we increase alpha? By simply, we don't have to pay very much to do this. We just go into the word processor and we change the standard. Notice how when alpha gets bigger, power gets bigger? We can say, you know, instead of setting alpha at 0.05, let's set alpha at 0.10 or 0.15, which amounts to lowering our standards. Let's accept basically all sorts of unsafe. Let's increase the probability of accepting and certifying unsafe TV sets. And that's option 4. The company could increase alpha, effectively lowering their standards. Let's increase the probability of a type 1 error. Let's increase the probability of incorrectly rejecting the null hypothesis, or incorrectly certifying these stands as safe, or what is required to certify the stands as safe. This is a big risk, since there's a greater chance of a type 1 error where children get hurt, namely allowing unsafe stands to be sold. We are talking low cost here. All we gotta do is change our paperwork. We have lower standards now, and it's high risk for children. Let's do it. Let's do this one. Let's lower our standards. That's the easiest way to increase power. However, it's unethical. Just trying to be funny here. That's really not the way to go. And now for our last example, number 31. Students investigating the packaging of potato chips purchased 6 bags of Lay's Ruffles marked with a net weight of 28.3. We know that's not true. It's not exactly 28.3. It's either a little bit more or a little bit less. But we're going to carefully weigh the contents of each bag, and our sample size is very small. Just like William Gossett at the Guinness Beer Company often used small samples, we are using the sample size of n equals 6. 6 is less than 15, so this is a bona fide small sample. The randomization condition, these are randomly selected bags. 6 is less than 10%. Okay, they're not really going to check for this, but technically the 10% condition is passed. Nearly normal condition, you have to make a histogram. You actually have to take these 6 numbers and go, okay, there's 3 of them in the interval 28.5 to 29. Only 1 of them is in this interval, 2 of them are in that interval. Look, unimodal and symmetric, so we're good to go, nearly normal condition. Now, let's see how to use a calculator to get the mean and the standard deviation. So, take out your calculators now, and let's go to stat edit and type in these numbers. So stat edit. And I'm going to try to get these numbers up toward the top so I can see both at the same time. So this is a good example of something that you're going to have to do on next Friday's test. So we go to edit, and I'm going to go to list 1 by putting the cursor on list 1, clear, enter. Let's type in these 6 numbers: 29.3, 28.2, enter, 29.1, 28.7, 28.9, and 28.5. So we have those entered. So if you go stat calculate one variable statistics, the calculator gives you the sample mean and S. So X bar and S, which are printed on your paper, I think. Yep, those were produced by the calculator using one variable statistics. Bell just rang. You stay in the room. That's not your bell. And now let's go to the last one. It says create a 95% confidence interval. And that's on the next page here. So just skipping ahead to the last section, 95% confidence interval. Here's what I would expect you to do. Since the conditions for inference have been satisfied, use a 1 sample t interval with 6 minus 1 is 5 degrees of freedom, 95% confidence. You got to show your work. And the t star 5, that's going to come from inverse t of what percent, so 0.975, comma 5 degrees of freedom. That number will put you in there, and you'll be able to get this confidence interval. Now, it says also find the interval on your calculator using stat test. So we're thinking A, B, 80, 56, 24. So that'd be a stat test 8 would give you the same answer. So explain in context what this means. It means we're 95% confident that the mean weight of the contents of Ruffles bags is between these. Does that contain 28.3? Since the interval is above the stated weight, or in other words, 28, both teeth are above the hypothesized value, then there is evidence that the company is filling the bags to more than the stated weight on average. It's important terminology there. So you're dismissed. See you Monday.